So hi there, my name's Douglas Elliff, and as the sort of acting crypto pseudo pretend dean at the moment, it's my great pleasure to welcome you to the inaugural lecture by Professor Michael Witbrock. Michael's a relatively new appointment at Auckland, having joined us just about 2 years ago now, I think. Slightly more than 2 years ago now, having previously been a distinguished research staff member at IBM's TJ Watson Research Centre in New York. He has a BSc in Honours in Psychology, good, from Otago University, and just saying to me now, his family have been in New Zealand for 170 years, which is impressive. And his PhD is in computer science from Carnegie Mellon. Michael is a very influential figure internationally in artificial intelligence, with around 150 publications that have been cited well over 5,000 times. I don't mean each of the 150 has been cited 5,000 times, but in total. Michael is rapidly building a very innovative research group here called the Broad AI Lab, and it's a testament to Michael's judgment, or at least I think it is, that one of his first hires was one of my former PhD students. Hello, Josh. Nice to see you here. You're on to more interesting things. The group is focused on machine learning and reasoning and natural language understanding, with a particular interest in the social and civilisational impact of artificial intelligence, including immediate benefit to New Zealand entrepreneurs and businesses. There's a very applied focus here. From Michael's abstract, we're going to learn something which I'm finding a great relief, which is that humans are better at thinking than rocks are, which is a good thing to know. And the idea that we can conceptualise new ways of thinking as software upgrades is, I think, a particularly sort of intriguing idea to me. And the idea that, again from Michael's abstract, that these upgrades come with costs as well as benefits seems sort of worryingly familiar. Microsoft, anyway. The abstract for Michael's talk is as fascinating to me as for any inaugural lecture that I've introduced. And I'm looking forward very much to the next half hour. Please join me in welcoming to the stage Professor Michael Witbrock.
Thank you very much. So now I'm wishing I had read the abstract before writing the talk, but hopefully you won't be too disappointed. Kia ora koutou, ni men hao, good evening. I'm going to talk about my what I think about thinking and how it might change. So sort of when you think about thinking, there are three things that I think you should think about. So one thing that's kind of important to consider is, like, who's doing the thinking, because what constitutes thinking really depends on who's doing it. And you kind of think of thinking as something that is done. You may think of thinking as something which is done by an individual, sort of in isolation, producing some product of this thinking, which are thoughts. Right, but I think that's kind of a unfairly restrictive view. It's unfairly restrictive on the low end. This thing here is a plizia. It's very slightly smarter than a rock. We know the complete circuit diagram of its neural system. It has about 10,000 neurons or so. It's been very important in understanding the physiology and genetic physiology of thought, but that is much less intelligent than your average neural network, and, as I said, slightly more intelligent than your average rock. If you're worried about eating that, don't be worried about eating it, because it's smart and might care. Worry about eating it because it's disgusting. That thing there is a Kia. It is much smarter than a rock. There is Ada Lovelace. She is also much smarter than a rock and much smarter than a Kia. But they are both capable of. They're capable of thinking at an individual level, and they're kind of most famous in a way for being able to think at an individual level. But it's not just individuals which think, right? For humans, because we're the partially eusocial kind of animal, when we get together, we're much better at thinking than we are individually. So we do things like form labs. Well, I'm doing that at the moment. It remains to be seen whether we're better at thinking than we would be as individuals. But when we can form like larger groups, We can form very large groups. This is where I used to work. I used to work there. This is the IBM T.J. Watson Research Centre. It's a very large laboratory which is part of a very large company, and you can think of a company as an organism, right? You can think of people groups in general, from teams up to groups up to large organisations, and especially corporations, as things which think. And they think very much better than individual human beings in some ways. And then what we're building at the moment is sort of this planetary thinking thing. Those are some Starlink satellites which will join all this planet up into one thing that is capable of thinking, but also might be capable of thinking sort of dangerous thoughts. So the second thing to think about on top of who's thinking is like, what are they thinking with, right? And so traditionally the thing that you thought with is a monkey brain. Well, actually it's a chimpanzee brain, so that's unfair to the chimpanzees. A human brain, a cute little 6502 processor from my childhood. That's not actually my one, I didn't have time to photograph it. Quantum computers, optical networks. Optical networks are something that's worth thinking about in terms of the great difference between them and people. People are very slow compared to that, and they're like extraordinarily slow compared to that, unless you're Roger Penrose and think otherwise. This is a GPU, so it's a fairly modern type of computer, and that we won't mention further, even though I'd intended to. That's a Neuralink machine. Just isn't going to be time to talk about sticking wires of various kinds in brains. And the third thing to think about is like how you're thinking, right? So there's things that think. There are things that you think with, and then there are modalities of thinking. And in things like human beings, there's this guy, Daniel Kahneman, who wrote a book, Thinking Fast and Slow. He's not the first person to have thought his thoughts, but he is the first person who wrote a book which was as popular. And he divides thinking into system 1 and system 2. System 1 is the sort of thinking which is keeping me upright at the moment and identifying Dr. Alice there. And it's the Professor Alice, sorry. He's been inaugurated too. It's done rapidly unconsciously. You don't know that you're doing it, and it's not hard, right? System 2 is kind of thinking slowly and carefully. It's the human superpower, not just humans, Kias as well, octopuses, a few other things do that seem to do that kind of slow reflective thinking, which counts as reasoning, but it's super powerful, right? It's the reason we're sitting here with gadgets, right? Other creatures don't make gadgets. Well, crows make gadgets, but they're sticks, right? So, but it's done really poorly by most people. It's really valuable. It's the thing that drives our civilization, and we're really bad at it. So the theme of this lecture is how might we as a people group get better at this, even if individually we can't. So if you're good at that, you get paid well and people inaugurate you as a professor. You don't even have to be good at it. And that thing is the fundamental design principle of computers, right? So the abstractions that we form when we think about type 2 thinking are the reasons why we have these things, right? These binary numbers and logic and reliable memory systems and so on. They're all based on kind of a simulation of this kind of thinking, although nowadays we're a little bit blurred. Right, so I said in the abstract, so I did skim it, that we'd talk a little bit about how humans have thought over time and how that's changed. So if we start off thinking, right? We started thinking in kind of the same way that we might think that a Kia thinks, or other kinds of simpler people like chimpanzees might think like this, right? So mostly from sensory data, right? So you see stuff, you do trial and error, you eat eat stuff and it's good, or you try poking at something with a stick and it works and you keep on doing that. It's done sort of one human at a time, one problem at a time, and the benefits of this are only shared directly, right? I can go off and work out that I can hunt potatoes or kumara, right? I can dig them up and I can take them home and you get to eat them and that's wonderful. But if I can't communicate with you, right, all you do is get the kumara, right? I can't teach you to fish kumara on your own, or whatever the metaphor is, right? So that's kind of not great. And while we were stuck in that state, we did not do very much better than the other animals. In fact, up to the point where we got beyond this, our primary advantage over other animals is that we could run away from them better than everybody else. So humans are very good at thinking, but we're also very good at running away. So we can run away for a long time, and that gives us an evolutionary advantage. Right, so we're in the state for a while, but then there's sort of a transition, right? So, and in between, before we got out of the state, we were able to do things like imitation. I believe that crows and kia can also do that. If one of them learns to do a stick, the other ones can watch them and they can learn to do that too. So that's a way of transmitting information by kind of simulating, in much the way that a reinforcement learning system might do now, simulating the action in their brain while pinning it to some observed data to make it the right action and then doing it themselves. So we could do that. Part of what comes along with that, in order to do that, you have to have some kind of theory of mind, because you have to recognize that that thing is doing something that you might do, right? So you have to see it as an analog of yourself. And because of that, limited collective action is kind of possible, right? You can run with your band, you can all run in the same direction. You can see that people are hitting the wildebeest in 2001 with the jawbone or whatever it was. It wasn't a wildebeest, it was something else. Anyway, whatever the animal was, yeah, you're hitting it with the jawbone and it falls over and you all descend on it as humans do. We are not nice creatures. On the other hand, the creatures which caused us to get so good at running away aren't all that nice either. So eventually we stopped doing that, right? Eventually we invented language. That's great, yeah. That was the best invention that we ever made. I don't promise to be consistent about thinking that's the best one. Sometimes I think that those automatic towel dispensers, which you put your hand under and you don't have to touch, and which the university eschews the use of in favour of things which spread germs. But anyway, sometimes I think they're the best invention. So we developed language, which entails the development of concepts like a glass of water, and I think this is probably for me. Yes, thank you. There's a general concept of a cup here, and it's a container and so forth, and these things we can compose together and we can say things about it, and that's really useful because the next time a cup comes along, I can decide more reliably whether it's a cup or not. Right. So this allows, language also allows us to transmit information not individual to individual, but sort of reliably from an individual to small group. And because of that, because each of the members of that small group can go and transmit their information to another small group and so forth, we can get exponential knowledge spread. So that's much better than linear knowledge spread, right? With that, in a lifetime, you could spread a piece of knowledge to all the humans, which back then, there were not very many of them, maybe 100,000, right? But you could easily cover all of them, apart from some of them were kind of far away, right? Could develop counting. As a result of the ability to share this knowledge, we could have cultural artifacts like agriculture and navigation. We could start developing abstractions about thought leading to this talk. We could do things like develop rhetoric, tikanga, law. We could plan together, right? We could build parts of plans serialize them out, as we say in computer science, serializing them into other brains, change them, and do that repeatedly to build a plan which was the product of more than one of us, a thought which had been constructed by a group. This was a great advance. But the problem with doing that, is that it does you no good after you're dead, right? All that stuff goes away. And back then, that map is like when you were dead, and not very long ago. So in our lifetimes, we have approximately half the probability of being dead at some point in starting from your birth, right? So that was a bigger problem for them than it was for us, and it's no longer a problem for us. So, yay us, right? And because we invented knowledge permanence, otherwise known as writing, right? What writing allows you to do is to stay around after you're dead, or at least your thoughts can stay around after you're dead. That's very useful. It can be, and your thoughts can be accessed at any time, even when you're asleep or dead, right? They can be unchanged over generations, but you can write new things based on them, so they can be modified. They can be modified, and you can keep checkpoints, just like Google Drive does when you drop a file in it. Remembering what you used to think, and there's no limit to the amount of accumulation. Well, I suppose there's some limit, but our disk drives have very small features on them. So, if we turn our solar system into storage medium, we're going to be able to store quite a lot of stuff. And for the first time, it's put a physical technology into the path of thinking. So up to this point, we had psychological technologies like rhetoric and quite sophisticated theories of rhetoric. We had psychological technologies like tikanga, right? Like notions of what the right thing to do and the wrong thing to do in a culture are. These all improved our ability to think as individuals and as groups. But this writing was the first physical technology of thought. But we didn't stop there. Yeah. So this sort of allowed us to start moving towards other ways of improving thought. It allowed numeracy and record keeping, which allowed us to build larger kind of groups. It allows the joint development of knowledge when separated, right? I can write down part of a plan and send it on a person or an animal to you, maybe a pigeon if it's light, and you can augment it and you can send it back, and we can build up through this email thread. We can write our grant proposal to the Paleolithic granting agency, and that means it was the first non-local networking technology, right? So this was the first the first thing where we were sending bytes around the world and kind of building up composites of permanent knowledge. So that was really, really useful. And again, it's like unlimited accumulation over generations, which means not only can we build up thoughts from people who are widely distributed in space, we can also build up thoughts from people who are widely distributed in time. We can build things with people who are dead. And that was useful. And now I think we're at the stage now when we can build the first little bit of our inevitable path towards artificial intelligence, right? So at this point, we can start really building long-term abstractions about thought, right? So artificial intelligence is really kind of the technological embodiment of of abstracting thought from our minds and realizing it in other ways, right? So when we formalize thought, we are doing something which is on the path to artificial intelligence, because we're kind of making thought, we're manipulating an abstraction over thought. Right, so won't worry too much about that. This is Aristotle's organon, one of the, and we still have it because we have writing. And this was one of the first publications about logic. And logic has been important in the history of artificial intelligence, and one of the goals of our lab is to make something like logic important again, because it's not fashionable at the moment. Right, so logic, speaking of logic, inference. So inference is this process of formalizing reasoning. So we all do various kinds of reasoning, but it might be good reasoning, it might be bad reasoning, our conclusions might be reliable or unreliable. It's kind of hard to tell. People go around making all sorts of unreliable inferences all the time. It's quite the fashion these days. And then they go on YouTube and tell other people about it, or Twitter. We get ourselves into messes so far that we haven't got ourselves into redeemable messes, but we have ended up having a lot more people dead from COVID, for example, than we needed to because of unreliable inferences. Right? So some of us don't like this about ourselves, right? That our inference methods are unreliable, and we would like to, where possible, be able to conclude things and then trust that no matter what happens, no matter what other things people might think or whatever opinions or whether they're happy or sad, those things should remain the same. That's a big thing to ask for, and I'm not, unofficially, I am not so sure about its prospects for widespread applicability, although people try. And it's really hard to do, and it's really, really hard to do for people. Logic is just. Don't even try it. So it's just no fun. All right. So, it's what it is. It's a set of reliable cognitive technologies of various sorts. Perhaps partially mechanical and partially sort of psychological or philosophical, which allow us to combine knowledge into new knowledge, where we can rely on the new knowledge at least being no less reliable than the knowledge which was combined. Right, and that's pretty good, and this leads to our ability to have philosophy. It also leads to our ability to have case law, right? So you can examine a case and you can test that case with respect to carefully constructed language, a kind of logic, which allows people to fairly reliably reach the same conclusions given the same information. That means that we can actually use individual cases filtered through this function of case law to build up a body of law over time. This is no small achievement. We'd like to do more of that kind of thing for more fields by teaching computers to do it too. We can have things like mathematics and accounting, scientific method, logic and professions, because we are able to formalize these reasoning processes to some degree or another. Right. So once you've developed that, it kind of allows you to develop other things on top of it, right? So one thing that you can get once you have these formalized reasoning techniques, these systems for inferences, that you can take kind of dodgy teachers and cause them to be able to educate students reasonably well, because you can tell, because there's a method for telling whether they've taught them the right things or not, right? So this enables universal education. The utility of this sort of inference has led to us trying to teach everybody to do it. And as I said, like, humans are lousy at this, so good luck with that, but still we strive. And there are 40,000 people who think that they're being taught to do more reliable reasoning or something here. Leads to sort of meta professions, so you can sort of analyze the behavior of professions like doctors, for example, and see whether or not you can codify what they do in ways which will improve their reliability. So for example, those checklists, when they're always asking your name and your birth date and so on, that is an attempt to apply a kind of logic, an organizational logic, to the profession of medicine in order to improve its reliability. The reason I care about organizations quite a lot is that I think that organizations are a better model for AI systems than individual human beings, just because of the fact that they can do complex reasoning in parallel, for example, the fact that they rely on inter-processor communication extensively, all things that are that AI systems will necessarily have. It leads to franchising. And I haven't been talking about this, but down here in the thing is the kind of the kinds of things which are most affected by this kind of thinking, right? So by the time we're up here, we've moved on from people and small people groups and teams and so on to the things which are most affected by this are abstract persons like universities and whole civilizations, right? The idea of a meta-profession only makes sense at a kind of civilization level. All right, psychology. Yeah, so psychology again is a technology for upgrading our thinking, right? This is where we look at how we think, right? And we look carefully at the mechanisms for how we think. Not really so much about the content of the thoughts, but the mechanisms both at the level of computational abstractions, right? Motivational abstractions, but also sort of abstractions of the of what goes on physically. And these are a bunch of historically relevant psychologists somehow connected to the topic of my talk, and I'm not going to go into much more detail, although this is a picture illustrating long-term potentiation, and I have a particular fondness for that because when I was a psychology student in Otago, I stuck electrodes in the brains of rats and tried to make that happen. This is one of the first theories about how to update weights between neurons in order to have a general learning algorithm, and long-term potentiation was a mechanism which embodied the sort of thing that, so this book was written in 1948, right? So a very long time ago. Clever guy, this Donald Hebb. And long-term potentiation, because I was doing it as an undergrad, must have been invented around 1980. Because it had just been discovered recently. That's not actually a Skinner box, but everyone calls them that now, so we'll let it go. Yeah, and that leads to the second part of the roots of AI, which is sort of how does computation actually happen inside intelligent organisms, and how can we replicate that by simulating it on computers, right? And this is one of the first reliable diagrams of part of a human neural system by this again very clever guy, Santiago Ramon y Cajal. It was a beautiful picture as well. So we've been trying to make AI for quite some time now, right? Some reading back to Aristotle and beyond, on some reading back to Ramon y Cajal. Certainly by the time Donald Hebb came around, the Turing test had already been invented, and we were well on our path to making intelligent machines. And the last kind of maybe it's not the last kind of thinking, let's not be bold, I don't remember. But meta-civilization, right? This is a new kind of thinking that applies at the level of whole civilizations and has become necessary recently, right? And I think people don't like it when things become necessary, but they do. Thinking about whole civilizations, right? When you're forced to, because the whole civilization is rapidly interacting, causes you to come up with new ways of thinking. So one of the new kinds of ways of thinking that has been born because of this is cultural theory. There are many people who don't like that. Too bad. I'm not saying it's right or wrong. I'm just saying that it's a thinking that way is a natural consequence of the situation that we find ourselves in, and we should not act surprised or upset that people are thinking that way, right? Similarly, it has led to things like international law and intercultural law. So, for example, the Outer Space Treaty and the Treaty of Waitangi are both examples of that, and were so forced upon us, this sort of thinking, which was novel at the time, somewhat novel at the time, was forced upon us by the fact of our technological and social advancement, our movement from isolated groups, from individuals towards whole civilizations, right? This is one of the main threads in our upgrade, in what we've been able to upgrade ourselves to be able to do because of upgrading our thinking. Similarly, it's led to the idea of human rights. You need that idea if you're going to manage people by the millions or the billions. You don't necessarily need that idea. You'd still want that idea, but you don't need it, right, if you're just managing a village. And macroeconomics similarly. You don't need I would say Marx, but I can't remember the name of that the Austrian economic guy on the other side, Milton Friedman, and the likes. You don't need Marx and Friedman if you don't have large societies interacting with huge money flows, right? You don't need this type of thought without that. So civilization scale thinking is developed, and then, along with all of this, the important piece perhaps for this talk is thinking with machines, right? This is a new kind of thinking as well, and it's again, I would argue that it's necessary because it's the only thing that can successfully run the sorts of thoughts which are required for the things in the last slide. So for example, if you're thinking about civilization level thinking, the maximum output bandwidth of a human being is some few kilobaud, right? Remember kilobaud when things used to come, yep, that doesn't happen anymore because they are doing that at frequencies of billions of hertz, right? So we can't hear them doing that, but they're still doing it. And your computers can talk to each other at of the order of 1 billion words a second, right? We can't do that, and there are some kinds of thinking, I would say, that you can't do unless you can talk to one another at that rate, right? So there are types of thinking that human beings, at least without brain-computer interfaces, will never be able to do because our network bandwidth isn't large enough or parallel enough. So yeah, we've been building thinking machines for a long time too. That one's that Greek one from in the boat, yeah, so we've been trying to do that for a long time, and we're getting better at it at what I hope is the required rate. So part of what that's enabled us to do is have broadcast knowledge, right? Because we have machines like radios. We have a lot of radios and even more cameras, ridiculous numbers of cameras in the world. Actually, I don't know, this might have more radios than cameras. It's got all sorts of radios for things you don't think about. We developed technologies for broadcast knowledge, printing first, radio, TV, web, Facebook, YouTube, TikTok, and who knows what's next. Eventually something involving putting stuff straight into your brain will come along, because I had some anesthesia related hallucinations, and they had great resolution, right? I mean, those things, I mean, they were just like wallpaper patterns, so they weren't very interesting, right? But they were better than TV, and our TVs are really good these days, right? So, all right, we'll get to that. And then another thing that we've developed along with, those technologies were all about getting stuff out to the humans, right? But we also have data broadcast and exploitation. And again, that allows us in principle to do sorts of thinking that we weren't able to do before. So for example, it's conceivable that you could have a computer read all of the scientific papers that have ever been published and talk to other computers about them and see which parts of them are consistent with each other and which parts aren't. We need that, right? We are at a point in science where the humans can't do it. We need to develop that. That's one of the things that I'm hoping the sort of technologies that we're developing will lead to. Because at the moment, it's, I don't know, it's not quite just luck, right? There's peer review and so on, but the probability distributions associated with all of our paper-to-paper information matching technologies have extremely high variances on them, and we've got to reduce that, and I think the way to do it is automation. All right, so we're still doing okay. Yeah, so what's the solution to this, right? Jump to the end. Automate the whole process: data collection, augmentation, knowledge, data adaptation, inference, checking and explanation, development of new AI techniques. Hand it all over to machines and free the humans so that we can go and don't have to give talks like this, which we'll get to in a bit. And I could have had a glass of wine before and had a nice relaxing time sitting with you watching a computer give a talk about this and everything else. And this is kind of the end point, right? Where this is going to happen this century, that all of the useful things will be done by our civilization without pretty much involving human beings very much in doing it, except for to the extent that we want to be involved, and the extent that we're not going to mess things up in ways which really can't be allowed. Right? I mean, there are some things which, there are some things that human beings cannot be allowed to do. Controlling nuclear weapons is one of them. Synthesizing viral genomes and encapsulating them. It's like, no, do not let humans do that, right? But we'll see. So we need to find ways not to do that, and yet we need to have the technology, all the technologies required to synthesize viral genomes and encapsulate them, because that's like this distance away from how we built the COVID vaccine and how we built it so quickly. Right, so we need to be able to do that, and we can't let ourselves do it. This is a little bit of a worry. All right, so we're going to hand this all over to AI. Well, maybe not, but that's one thing that you might think about doing. So what is AI, right? When I started in AI, people thought it was funny to say that it was everything that we don't know how to program. But now AI systems know how to do a lot of things that we have not, there's no hope that we'll ever know how to program them explicitly, right? They are too complicated. In fact, when it comes to, for example, playing chess, we don't even know how to play chess anymore, right? We're no good at it, we lost. How the hell are we supposed to write a program to do something that we can't even do? Right, and the number of things which have that quality is not going down. It's going up. So AI it started off kind of slowly. Logic, neurons, Hebbian learning. People did stuff. I started being interested in it about. I read a book called Machine Learning when I was a little kid, and by I don't know, then I guess I was working on it, although not on psych at the time, although I did have a lost decade actually working on that thing. But it sort of went along, and people built programs which did sort of thinking-y things, right? And that was good, and grant money came and went, and there were AI winters and summers, and at that point, in 1971 and 1986, backpropagation was invented by different people. This one caught on. This is common in science because, as I said, we human beings are incapable of keeping track of it all, and it's not getting any better, right? So went along, and then all of a sudden we got this neural network stuff started working, and it started working. It started working for three major reasons, which I won't go into. I'll go into one of those, maybe four major reasons. See, I can't, because I'm a neural network, I can't do math correctly either, and neither the new ones. One reason was that we got good at storing large amounts of data and shipping it around. So data became free, that was really useful. Information retrieval became free as well. That was really useful and is not often sort of sung about very much. We developed something called a ResNet that you don't need to know about, but it meant that our neural networks could stop being small like a plizia and could go to hundreds of layers deep, which is deeper than most parts of a human brain. There was the development of Reinforcement learning, effective reinforcement learning, that took a while, but it came along. That's the reason why it means that you don't have to have training data. You just have to be able to tell whether you're right to some degree, right? It can even be probabilistically tell that you're right. And then you can learn to do things. That's why computers, that's why a human being will never beat a halfway competent computer at chess or go again, right? Because of reinforcement learning. And the last thing is the current thing which is doing really well, things called transformers. And that's why when you listen to a YouTube video, often you can tell that it's not a human being, not because the voice is funny, but because it's reading something written by someone who doesn't really speak English in a perfect American or English accent, right? So, and it's also the reason why, say, Google Translate is better at any language which isn't your native language than you are, and probably for most of you better at your native language than you are, right? It's because of these transformer networks, which we'll talk a little bit more about. Right, so transformer networks. So this is a little bit old. This is from 2019 or something. And it's a system called GPT-2. So it's hopelessly out of date. But one of these is the coloured writing. One of the pieces of coloured writing was generated by Shakespeare. One of the pieces of coloured writing was generated by GPT-2. Okay, so now you should, I'll give you a few seconds to decide which one you think is Shakespeare, GPT-2, Shakespeare, right? Make up your mind. Can you tell? You probably can't unless you've been to this. And this is one of Shakespeare's not so good plays, so hopefully you haven't memorized it. Right, this is from GPT-3 Da Vinci. This is a state-of-the-art system. I did this at 2 p.m. today. So this is my abstract. But actually, up to the point where it becomes fat and orange is my abstract. After that, it was written by GPT-3. Okay, this is in fact my abstract. And I've coloured a piece in red there and blue there, where we seem to be on the same page, me and GPT-3, right? So it's hard to tell that that wasn't written by a person. Now, I do admit that I went through 4 iterations of trying slightly different things and slightly different stopping points inside my abstract to find the one where it didn't spit out like a fake speaker name and building, right, and stuff like that, which is confusing. But this is, this is very lightly curated, right? So, yeah. So, GPT-3 thinks I'm dumb, or at least, and it took of the order of 2 seconds to write all that. So, yeah, and it's busy serving stupid requests like this from millions of other people at the same time. So there you go. And the answer to the question before is that the one on the left is from GPT-2, but who cares because it's obsolete. GPT-3 laughs at it. We could prompt it to do so, probably. All right, so that's really quite impressive, I think. What these AI systems can do. If I went back to 1990s me, let alone 1980s me or 1970s me, and asked whether or not these people in 2020 had artificial intelligence, I think I would have to say yes, right? And this isn't all that we can do. We can take an old photo of someone and raise the resolution and animate it and make it say stuff. We can take a half picture of a kitten and fill out the other half of the kitten. We can tell a system that we want a picture of an avocado playing chess and eating a banana, and he'll draw some cartoon to that effect, and we can be beat at an increasing number of games. And we can synthesize art and stuff. All right, so all sorts of stuff. Apart from kind of apart from sort of agency, I think, is that we would have thought was definitely AI has happened, and I don't know. It's kind of difficult to deny GPT-3 like a tiny little bit of agency. I was going to tell you how GPT actually works. But it's not intuitive enough for me to make it intuitive enough for you yet. And also, I don't think that would help, because if I told you how your brains actually work, it wouldn't necessarily allow you to judge whether you're intelligent or not, right? So if you look at neurons, they don't seem very clever, and right. So we look like we're winning. So maybe we're not winning because all the knowledge that we are storing away. So GPT-3 knows a lot of stuff, right? It wrote that without plagiarizing. It didn't go and look for anything. It just looked at its neurons and voila, right? But all that knowledge is in opaque parameters, which is true inside your brain too. Your brain. Anyone here who has non-opaque parameters in their brain? And we think they're not, because we have a special GPT-3 in our brain for confabulating reasons why we thought stuff, which I think we can reproduce for computers. So we'll work on that. There's lack of transfer between tasks. So this is becoming less true. For some tasks, like language translation, we just teach them to translate all of them, and they're better at each of them than they would be if they were just doing one. So there is some transfer, but sort of general transfer of task capabilities is not there. And what else? Yeah, lack of explanations, but I already denied the credibility of human explanations, so there's that. So what do we need to get to human level knowledge use, right? So what we want to solve those problems is for our AI systems to act as if they have knowledge in the same way that we do, right? To remember things, to say that this is the basis of my answer, to reuse the basis of that answer for future answers and so forth. Well, yeah, this stuff, because we can't realistically scale up this sort of careful inference, this like very careful legal thinking, for example, or very careful scientific thinking. We just can't do it by growing more people, because even if we grow more people, the network doesn't improve. The only way we can really scale that up massively is by automating it. So and when we are able to do that careful thinking, it's very good. Our buildings don't fall down. People don't die, right? People take the vaccines. People are not denied their property because some judge had a bad day, right? So that sort of careful thinking is very powerful. It would probably be good for us if we could have more of it done. So how might we do that? Now, one thing is to get to have more symbolic knowledge. Right, in some sense of symbolic. I mean, symbolic knowledge are representations of things which allow you to think about them more reliably. And there's a wide variety of symbolic knowledge. People who know what it means would usually think of it as denoting things like mathematical logic and computer programs, but it's more than that. So careful legal knowledge, for example, it's kind of like a computer program. It's a computer program for humans, which is designed to make them produce the same inferences about a legal case as other humans, right? But it's a more informal programming language because it's for humans. Similarly, formal narrative is less formal than formal legal language, and less formal than fiction. So when I talk about we need to get good at processing symbolic knowledge, and if we want it to be more reliable, we need to get good at pushing things down towards that end, right? So where we can take a mathematical logic, a mathematical notion, and push it down to mathematical logic, then we can be certain about it. So the more things that we can do that for, the more reliable our civilization will be. And it's not just, symbolic knowledge is not just about text. There's also all sorts of picture-like symbolic knowledge like that. And again, if we can push for useful purposes, right? As opposed to enjoyment purposes. If we can push things that way, we tend to get better results. And we can also push things that way and get more artistic results based on the facts. Both of those are potential things that machines could do. So we've got pretty good at learning. We've done a lot of research in the past on reasoning. This is from that time when I was doing psych. So that's an explanation produced by a computer about a case based on some complex reasoning. It's just that was very hard to get a computer to do. And I think that the best way to get computers to do more of that is to teach them to teach themselves to do that. But combining this sort of symbolic reasoning with the machine learning, which has been doing so very well recently, and this is from 2014, so you're totally unimpressed by it now. But back in 2014, that was impressive. Getting good at this stuff requires you to be able to take a problem that you're trying to solve, break it down into sub-problems, break that down into sub-problems, find the answers to those sub-problems, and then compose those answers back up into an answer. Here's a simple example. I'm not going to go through it, but this allows you to prove that Honolulu is a city based on something, population, based on it being bigger than Dunedin, because that's kind of my criterion. But than Dunedin when I lived there as a child. Yeah, that's where that constant 70,000 comes from. Right. So we're trying to, that's kind of our program, right? Make computers able to do at scale the sort of reasoning, the sort of thinking that we don't like doing because it's hard, and that anyway we can't do well enough because of hardware limitations like network bandwidth, the clock speed of our brains, which is about 200 hertz at the very, 5 kilohertz at the very, there's one kind of neuron in your ear which fires at 5 kilohertz, but that's it. That's the fastest. Do you know what computers think of 5 kilohertz? They think that is a decade, or I don't know, a decade in between firings. All right, so so we've got, so we're trying to do that, and we're trying to do that by carrying out a program of research, as one does, because we're at a university, and they won't continue to pay me if I don't carry out a program of research. Right, so one thing that we're trying to do is teach, this is a collaboration with the people at IBM Research whom I used to live with, and some of grad students, including Chiming there. So treat mathematics as a game. So the reason we won at chess was because of reinforcement learning. We are able to explore, given that there are a set of legal moves, we're able to explore those legal moves. We're able to tell whether we've won or not. Right? That's all true of mathematical proof. It's interesting to note that the majority of things that in mathematics that we think are true, we do not have machine verifiable proofs of them. Right? So the vast majority of mathematics is informal from the point of view of mathematical logic itself. So we would like to fix that and then go on from there. So this is, again, Aristotle. This is an early mathematical proof. That's a less early one. That's a fairly recent one about 4 colors and maps, which you may have heard about when you grew up. It was like done by enumerating a large number of cases because there were computers. But just like chess, a mathematical proof, you can tell when you're finished or not, but if it's a formally verifiable proof, you can tell whether it's a proof or not. So you can get a pellet, rewarding you if it's a proof, and nothing if it's not a proof. And there are moves that you can make, and those moves are use an inference rule to combine two lemmas. Two things that you already knew into a new thing. And though the set of those inference rules is small, the set of lemmas, unfortunately, is much bigger than the set of moves in a chess game or even a Go game, which is why this hasn't already been done. But but we're working on this. I expect this to work in the not distant future. I would be surprised if it takes 10 years to get computers better at mathematical proof than humans. And that will be useful. on a very different path. We're trying to at least think about what it would mean to build an AI system that embodies a cultural viewpoint. So can you build a system that doesn't just produce text, right, but produces text which produces outputs which reflect its membership in some way of a culture, a distinct culture or a distinct people group? And so what does it mean to have a Kiwi AI or an American AI or a Chinese AI? Not in terms of it speaks New Zealand English or American English or Chinese or Maori or Turkish, right? But because it's culturally situated, right? It's part of it embodies and implements the worldview of that group, or maybe of several groups, and the interactions between them. Can AI systems therefore, contribute to cultural coexistence by working out where the consistencies are and where the inconsistencies which need to be actively managed by people are, and to mutual benefit, and can they contribute to the cultures that they are embedded with? And because we're in Aotearoa, Indigenous cultures are of sort of particular interest in this respect. So we've got a couple of threads which are working in that direction. We're trying to learn to answer questions which require reasoning, Genuine in particular, and others are trying to do that. Zichi is trying to do that as well. So at the moment, there are a lot of systems which can answer sort of factoid questions really well, right? So if you have to combine two simple pieces of information, they can do that. If it requires more complex reasoning than that, and making intermediate results and then combining that, they tend to fall apart. Although something like that is clearly going on inside GPT-3, so it's why they don't do it is as much of a mystery as what they do. So we're trying to adapt these question answering systems so that they can do the kind of complex problem manipulation required to answer questions. We're trying to understand the sorts of reasoning that GPT can and can't do and why. So this is an excerpt from the paper, from the abstract that it wrote for me. And if you look at the green bit, right, a number of thinkers, blah, 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 while others, right? In order to maintain that level of consistency, that is an inference operation, right? Knowing that the arguments of those pieces, those frames, those syntactic frames have to be are compatible, requires an inference operation, but it's kind of uncontrolled. It's unknown which of those operations you can do and which ones you can't. And there's a whole industry of people who, friends of mine, who point at things that it fails to do and say, "Ha! You stupid GPT-3, you're not AI at all." Right? So we'd like to understand more clearly what the things are that they can't do, and then look at whether or not, for example, there are human psychological mechanisms which might be incorporated into these systems to give them those abilities. Similarly, the parallelism between those blue things is better than most of your first-year students. Yeah, it will get a better mark on the SAT essay test than a lot of people. All right, we want, so part of that is understanding what they do, but really what we want to do is make them reason. Clearly they're doing something, but if you give them quite simple tasks, actually the Winograd schema ones are no longer quite the sort of tasks they can't do, but you can give them quite simple tasks involving things like negation, and they get stuff wrong. If you ask them to add numbers together, they'll get it right some of the time, but not others of the time, and it seems to have something to do whether it's likely that there's been a table somewhere on the web which has those numbers in it. So like up to 5 digits, they usually get them right, and more than that, they don't, but we really don't know why. What we're trying to do is work out why they're broken in that way, and then give them general mechanisms which they can apply through learning. Right? So learnable mechanisms which will allow them to do those sorts of tasks more reliably. Yeah, so I poured the carafe into the glass until it was empty or full. What was empty or full? The answer, the carafe or the cup. Depending on which one you chose here, the correct answer changes here, right? So this type of problem, these winograd schema problems used to be really difficult. Now computers are approaching, I actually haven't looked at the leaderboard recently, they're approaching human performance on these sorts of problems, but it's not clear that that transfers to other tasks. We would like to transfer it to other tasks. These systems like GPT-3, they have read the internet, so they know they know a lot of stuff, including how to write my abstract, right? But they don't necessarily know. Suppose there's only like one example of some fact somewhere which is required to answer a problem. They can't do anything about that at the moment. There are systems which do information retrieval while they're doing question answering, but these have not been combined together. And even if you do combine them together, they wouldn't take the intermediate reasoning, whatever that is that they've done, store it away and use it later. So incorporating meaningful long-term memories and a meaningful theory formation, so that, for example, even if they read all the psychological or the molecular biology papers, right, to work out whether they're consistent internally, they couldn't really work out whether they're externally consistent because they wouldn't be able to build the abstractions which are needed to compare them, right? So this is something that we're going after. In fact, Josh is supposed to be working on something related to that at the moment. Right, so those are some research projects. Right, we're almost out of time. Societal impact. So doing things which could replace all the useful work done by humans is not without its impact on our civilization. On the other hand, like wiring us all up with satellites and fiber optics was not without its impact on civilization either. Inventing writing was not without its impact of civilization. It enabled, for example, mass religion for good or bad, right? So there are all sorts of effects. How can we mitigate them? So here's sort of what's coming at us over the next couple of decades. From large-scale reasoning, which leads to assistants that can do the sorts of things that, the sort of tasks that you would, if you were allowed to have a professional staff member help you, they would be doing for you, right? That is certainly coming. Better than human speech recognition is certainly coming, including the ability to hear things that you think can't be heard. Right, so that's a little bit of a worry. General conversational interaction is certainly going to happen. Better than human translation, just because they can read more stuff than a human could in many lifetimes, is coming. It's hard to tell exactly when. I'm involved in one effort in broadly capable robotics back in the US. Hard to tell when that's happening, but I have a feeling that we might be at about where we were in 2000 with cell phones. For robots, that they're about to become useful enough that there will be a positive feedback development loop, which will rapidly improve them. And then broadly capable of corporate AI, right? So companies that can mostly run themselves without humans involved, and then general superintelligence. Who knows when this is? I'd be surprised if it's not this century. I wouldn't be surprised if it's slightly after 2050, when there's almost nothing that involves kind of thinking that human beings are generally better at than computers. So we better start doing stuff about that, right? And the downsides of these are pretty bad. Right? Lots of constrained sensing and manipulation jobs, all the factory jobs go. Lots of constrained intellectual jobs, like answering email, dealing with the ridiculous forms that Doug now is responsible for foisting upon me. therefore, and if you lose those jobs, you get vastly unequal loss of resources, because the people who don't need people for those jobs anymore get richer. The people who used to have those jobs and don't get poorer. Therefore, broad job loss and broad loss of human control over corporations, in much the same way that we have, that various reorgs cause humans to lose control over the university. Similarly, that could happen in a much wider way, the end point of this sort of distribution from the people who are using AI. From the people who used to do what the AI is doing could lead to pretty extreme instances of rent seeking by corporations with AI, based on AI. And the worst case, the end point of that is that there's one company in the world, Goldman Sachs, which is entirely run by an AI for the benefit of Goldman Sachs, but nothing else, right? So this wouldn't be great, or zero. I don't know. If you want New Zealand to win, it doesn't really matter. And then the general inutility of humans, right, which doesn't have to be a bad thing as long as humans still have value, right? Relaxing is not bad. I've already shown you that I don't need to write abstracts for talks anymore, or at least I only have to write the first half of them. But that could lead to generalized loss of human autonomy. That wouldn't be good. Or the future can be really good if we maximize, if we use AI to maximize health, longevity, and justice, if we use it to maximize equality of access to resources, which means like changing our notion of ownership of them, means changing our notion of how you allocate resources, because you can't allocate them based on utility, which we don't at the moment anyway, right? But we can't do that at all. We can't even pretend that we're doing that. A widespread benefit from the economic and other products of AI, right? I mean, there's no reason why anything in this situation should cost almost anything, or nothing useful should needs to cost anything if you have this complete automation. Right, so this could lead to freedom of people groups, animals, and the environment. It could lead to AI systems which really understand the cultures of different people groups, gently managing the relationships between them and helping people to maintain more agreeable relationships while not being interfered with. Right, it could, that could lead to general increases in human autonomy and our ability to act properly as communities, which is something that we're really good at when provided the means to do it. And could end up with us, increasing the sustainability and then perhaps the reach across the galaxy of human civilization. Right, so Plan B is the one to pick. Right, so let's make that happen. And the future of thinking, which can lead to Plan B, definitely includes Aotearoa. We don't want you just to come to the University of Auckland and join the lab. We would like New Zealand to get better at cooperating to bring this together, right? Certainly the psychology department has an enormous role to play in, for example, helping us to learn what sort of things should be added to GPT to make it smart enough to reach these goals. All of the AI doing departments across the country can work together to achieve these ends and their own ends more quickly. Right? We can have an impact on this future, and I would very much like to see us do that. Thank you.